Hello everyone, my name is Pooja Mishra, college roll number 205076. My presentation topic is gradient, divergence and curl in tensors. Now let us understand gradient of a scalar. Let phi be a scalar or invariant. Its covariant x to the power I derivative is denoted by phi comma I and is defined as the ordinary partial derivative of phi with regard to x to the power I. Thus phi comma I is equals to del phi upon del x to the power I. We can write it as phi comma I is equals to del phi upon del x to the power I, which is equal to gradient phi. We can write it as nabla phi. Now divergence of a vector. Let a to the power I be a contravariant vector. The divergence of a to the power I is defined as the contraction of a to the power I comma I, or in other words, the contraction of covariant derivative of a to the power I is defined as divergence of vector a to the power I. The divergence of a to the power I is denoted by div a to the power I. Thus, divergent a to the power I is equal to a to the power I comma I. Now coming to theorem number 1, it says if a to the power I is a contravariant vector, then we have to prove that divergent a to the power I is equals to 1 upon under root g del upon del xi of a to the power I under root g, where g is equals to mod of gij. By definition, the x to the power j covariant derivative of a to the power I is given by a to the power I comma j. We can write it as del a to the power I upon del x to the power j plus a to the power p in bracket I pj. Setting j is equals to I, we have a to the power I comma I is equals to del a to the power I upon del x to the power I plus a to the power p I pi. Uh, uh, Now del a to the power I upon del x to the power I plus a to the power p, we can write the value of bracket as del upon del x to the power p log under root g. So putting this in this equation, we get del a to the power I upon del x to the power I plus a to the power p del upon del xp in bracket log under root g. Now we get del a to the power I upon del x to the power I plus a to the power p in bracket 1 upon under root g del under root g upon del x to the power p. Here we have differentiated log under root g, so we get the value of this derivative as 1 upon under root g, and then this derivative will be applied on under root g. So in the next line we have del a to the power I upon del x to the power I plus a to the power I upon under root g del under root g upon del x to the power I. By replacing dummy suffix p by I, we have 1 upon under root g in bracket del a to the power I upon del xi under root g plus a to the power I del under root g upon del xi. Which is equal to 1 upon under root g del upon del xi in bracket a to the power I under root g. Now divergence of a to the power I will be given as a to the power I comma I equals to 1 upon under root g del upon del xi in bracket a to the power I under root g. Here we have summed up for all the values of I, that is 1, 2 up to so on n. Now the second theorem states that we have to prove in this theorem that divergence a subscript I is equal to divergent a superscript I, where a subscript I and a superscript I are the covariant and contravariant components of the same vector A. So coming to the proof of this theorem, we know that the divergence of a covariant vector a subscript I is defined as divergent a subscript I is equals to g superscript j k into a subscript j comma k. So divergent a subscript I will be equal to g superscript jk into a subscript j in hold this in bracket and then comma k. Since here g to the power superscript jk is constant, so in the next line we have a to the a superscript k in bracket comma k comma subscript k will be equal to a superscript I comma subscript I. By replacing dummy suffix k by I, we have divergence a subscript I is equals to divergent a superscript I. Now in the third theorem, we have to prove that gradient of phi psi is equals to phi gradient of psi plus psi gradient of phi. So the proof will be as, by definition of gradient we know gradient of phi psi will be written as nabla in bracket phi into psi, which is equal to del upon del x del superscript I in bracket phi into psi, which is written as phi del psi upon del x superscript I plus psi del phi upon del x superscript I, which is equal to phi gradient of psi plus psi gradient of phi. So the theorem number 3 is hence proved. Now coming to theorem number 4, here we have to prove that divergent in bracket phi into a is equal to gradient phi into a plus phi divergent a. So proof we have divergent a to the power divergent a superscript I is equals to we know that 1 upon under root g del upon del x to x superscript I in bracket under root g a superscript I. Considering this as equation number 1, then we have divergent phi a superscript I is equals to 1 upon under root g del x del upon del x superscript I in bracket under root g phi a superscript I, which will be written as if we take common 1 upon under root g, then in bracket we have del x superscript I del x upon del upon del x superscript I in bracket under root g a superscript I and then bracket close phi plus under root g into a superscript I multiplied by del phi upon del x superscript I. We can write it as del phi upon del x superscript I into a superscript I plus phi 1 upon under root g del upon del x superscript I in bracket under root g a superscript I. So from here we can write it as gradient phi into a superscript I plus phi divergent a superscript I. So from here we have divergent phi a is equals to grad phi into a plus phi divergent a. So now the fourth theorem is proved. Now coming to curl of a vector, let a subscript I be a covariant vector, then we have a subscript I comma j is equals to del a subscript I upon del x superscript j minus a subscript p in bracket p I j. Interchanging suffixes I and j and noting that pij is equals to pji, we get a subscript j comma I is equals to del a subscript j upon del x superscript I minus a subscript p in bracket pij. Subtracting considering this equation as equation number 1 and this as equation number 2. Now subtracting equation 2 from equation 1, we have a subscript I comma j minus a subscript j comma I is equal to a del a subscript j upon del a subscript I upon del x superscript j minus del a subscript j upon del x superscript I. The tensor a subscript I comma j minus a subscript j comma I of rank 2 is defined as the curl of the vector a subscript I and denoted by the curl a subscript I. Thus, curl ai is equals to aij minus aji. Now, these are my references. Thank you.